Hello, good afternoon. Welcome to the conference for the deep dive in 1 gigawatt scale electrolyzer design today. Today we are in the studio in Amersfoort. My name is Carol Schell, a program manager at ISPT for the green hydrogen. Today I'm your host. Here I have with me Andreas ten Kate, my colleague, and also Hans van het Noorden is also my colleague. Andreas is our program director of ISPT, and Hans van het Noorden is our technical lead of hydrogen, and he has many years of experience in engineering and program management. Today, I would like to give the word to my dear colleague Andreas to explain to the audience and to you what is ISPT and why we started 4 years ago about the hydrogen program. Andreas, please. Yeah.
Thank you very much, Carol.
Thank you.
It's a great pleasure that I have the opportunity to introduce to you a little bit of where we come from as an organization and why we started this program. And I think we have a very nice program ahead for you. And this program comes from our organization, Institute for Sustainable Process Technology. Our organization exists for over 12 years, and what we do is we organize innovation programs for a sustainable process industry. It's important that in the energy transition and in general, we need to create a sustainable future, and the industry has an important role to play there. So industry needs innovation to develop new technologies and new insights for this transition. And what we do at ISPT is we bring all the parties together who have joint questions. So we bring them together, and we do this for many years. So because we work together with all these parties, they know us, but they also know each other. There's a high trust level. And this trust level makes that people are opening up on the questions they have and together go into investigations to learn more about new technologies. We all do this in the end based on facts and knowledge, and we try to expand that and develop new insights and knowledge, but still rooted in reality, so that what we find is factual information. And in ISPT, as an organization, with all of our partners, we do this in the end as an independent organization. So when we bring our results out, it has a right of its own to speak. And I hope that, again, today, with the report we brought out in January, and from today, you will get a bit of this flavor of working together, this trust level, factual information coming from experts in the companies themselves. And we're happy to share and bring this to you to expand and develop insights together going forward. So from this background, what's important is in the program that I'm heading, that we're doing together with our partners and our team, we look at system integration. And system integration for us means so much as how do we bring the renewable power that we need in the future to the industry, again, to make this industry more sustainable. And we have several sort of routes. And this picture is always the stronghold, the basis of our program. We look at how this renewable power, which will not be as continuous as we currently have from fossil-based power, how will we bring that to the industry, and how will we make the industry drive towards circular green value chains. So we have a program on hydrogen, the Hydrogen Innovation Program, but we also look at circular carbon, for example, how to recycle carbon, or we look at, for example, direct electrification and flexibility in the industry. These areas are very important. So the question that Carol asked, right, is where is this program coming from? And when we started our program, actually some of our partners had a question. They saw that somehow in the future hydrogen will be important, and they have some expertise in-house, but to prepare for understanding how this works with the flexible power, they wanted to do experiments with real electrolyzers. There's people from 2 large companies, our partners in the program, Shell and AkzoNobel, which is now known formally as HyCC for the hydrogen part. These 2 companies said, look, we want to really do experiments. Can we start a program on that? And then we brought more partners together and we say, okay, electrolyzers are nice, but what else is there to know? And we said, maybe it's good to think about how you go from one electrolyzer to a factory. And this was to start the first ideas of the program. That was the gigawatt scale electrolyzer project. And from there we said, well, we have to think further and look also what this electrolyzer factory then means in developing whole supply chains. And these 3 pillars, technology, scale-up and value chain, are the strongholds of our program. And currently we're even developing more insights and knowledge because, for example, we have a program that also looks more in depth into electrolyzers, the high scaling project, with a whole group of manufacturers. But we also look at, for example, the safety in large-scale industrial production facilities, which is a direct spin-off from the gigawatt project that we're sharing with you today. So from this background, what was very nice and what is very special about what we do is bringing these people together who, from their own curiosity and their own need to know, really work together and go in depth and share their knowledge to bring the result that we share with you today. So I hope that you will enjoy this session today. I hope you will learn a lot. And I look forward to meeting you at the end of this session again to see what are the key messages that we want to give to you and what we maybe can learn from working with you in the future as well. So with that, I think I will give the word back to Carol.
Yeah. Thank you, Andreas. It is really good to know that you started already 4 years ago with this program, which I have the honor to work with. I think you are really the front runner in this area, but also with our partners, because they believe that in ISPT and work together for that. Thank you. And I go back to the most important person in this project, which is Hans, who led us through this really die-hard, I have to say, project with the gigawatt design, because it's not a design you already have. So in that means I give the word from our technical lead for this project from Gigawatt, which was done by all our partners, and the heroes behind the scene are here today in the studio. But now we start with the overview from Hans.
Yeah, thank you, Carol. Yeah, I'm of course very proud to be here and to present the results to you together with our team. Clearly, the challenges are quite big to reduce the cost of green hydrogen, and that's exactly the thing that we are trying to achieve in this project, how to reduce these costs. Primarily, we look at CAPEX, but I can understand that a lot of people are also looking at OPEX. The cost of electricity are, of course, also very important. In this project, we focus on a conceptual design and cost estimate for a gigawatt-scale green hydrogen project somewhere located in the Netherlands. We are working with this group of companies as one team for achieving this goal of reducing costs. The special thing about this project is that we did a lot ourselves. We have managed to get all the experts, the engineers, the scientists from our partners working together in different teams, in different disciplines, different areas on these topics of optimizing, of innovating, and of improving processes. And that's what we have been done in the past few years, starting with a regional report on the infrastructure connections of integrating such a gigawatt-scale electrolyzer in 5 clusters in the Netherlands, looking at electricity, at pipelines for green hydrogen, and also water, cooling water, but also, for example, heat recovery and use of the excess heat in district heating networks. Then we continued with the baseline report on a state-of-the-art design of a plant which can be built today using technology which is available on the market. And that resulted in a so-called baseline design. And that was also the starting point of working towards an advanced design. And this advanced design, that is what we are going to present today, with all the facts and figures on how we manage to improve the design of innovating the stacks and in upscaling such a plant to a level that we can reduce the cost. The scope of the project is quite simply a greenfield facility connecting to a grid with an offshore wind park connected. And at the other side, we have the backbone and the connection to end-user facilities. And this picture shows you what it takes to build such a plant. We are doing that for Alkaline and for PEM. Here you can see how that looks like in reality, using a virtual reality model for an advanced plant which can be commissioned in 2030. This is again for Alkaline, and this is for PEM. And if you look carefully, you can see if I go back, that there are some differences in especially the water treatment. There's no need for mechanical compression for PEM, and there are also some changes in the separating section. But for the other areas, like the electrical installation, the gas treatment, the cooling water system, it's basically the same. Looking at the costs, you can see on this picture that on the left, the total installed costs, which are the costs that are important for an investor in a gigawatt scale green hydrogen plant, covering all costs. And at the right, you can see the direct costs, the costs which are for the contractors, for the suppliers of building such a plant. And that represents the 420 million that is indicated there for direct costs. And if you add the owner's cost, the EPC indirect costs, as well as contingency, you have the total installed cost. For Alkaline, that is 730 euro per kilowatt. And if you express that also in terms of production rates, then you can see it's 1580. In blue, you can see the figures which we calculated for the baseline design, which are roughly a factor 2 times higher. For PEM, these costs are slightly higher for the advanced design. As you can see, we are now at 830, whereas for Alkaline we were at 730 euro per kilowatt. But if you compare that also with the baseline cost estimate, then we were at 1800, and for the production rate was even higher. And that has also to do with the efficiency of the stacks. We also improved the efficiency of the PEM stacks. Then you can conclude. If we look at the areas where we achieved the cost reduction, then you can see at the left that for the Alkaline that we have basically find cost reductions all over the place, and for PEM as well, but as a very big stack here, so you can see carefully for the PEM stacks itself. So that's the 322 million, as I can see. It's very small numbers. Anyhow, we need to reduce the cost everywhere, and then we have also the factorized costs for the EPC and for the owner's cost and contingency, which also add up to a substantial amount of cost reduction. In today's webinar, we are going to show you how we achieved this cost reduction using innovations and optimizations throughout the entire plant. And I think that is what makes this project so special. We did not focus on one specific part. We looked at the integration of the system design with upscaling of stacks, but also of separators, connecting more stacks to one separator, having also larger modules, and also going to higher pressures, for example, for Alkaline, for example. And in that sense, we can say that we obtained this 50% cost reduction at the end of the day. We are going now to present you with all our team members who are going to introduce you to the different areas where we managed to get the cost reductions. And they will explain you how they did it. Going first with Professor Gert-Jan Kramer of the University of Utrecht, looking at the entire system, especially Electrolyzer, by down costs, and you will get familiar with this term in a minute. And then we continue with an explanation on the power supply system design by Nick de Koster, competence lead for Yara, and through the Teams connection also with Thomas Herskind from Ørsted, going to explain the power electronics, which are obviously a very important part of this conceptual design. And then we have Paola Granados from ICC, formerly Nobian, who is also going to explain what we did with the separators, and also showing you the material selection, for example, which was also quite important. We also have Thijs de Groot from ICC explaining the new novel stack design for Alkaline. And we have Arend de Groot from TNO introducing you with the PEM stack design innovation. And these are very, experts in their fields here in the Netherlands. We are very proud to have them in our team. And then we conclude with Rink Zwerve, Gasunie on the mechanical compression.
Yeah, thank you, Hans. I think you must be so proud of your team. So all the passion you have spread out. I think it's challenging to explain the story from 2.5 years in 10 minutes. You did very well. Thank you for that.
Yeah,
just a small question before we stop this block. What is your most surprising from the cost saving of this 50%? So 400 million of saving. What is the part that you were surprising by?
Yeah, I mean, when we started in the beginning, we didn't have too much expectations. Yeah, I mean, we thought let's look at the electrolyzers. There we will find most of the cost reduction. But it seems that the power supply and electronics is a very dominant part of about 25% of the direct cost. So any cost reduction that you can achieve there is automatically, of course, also important. But it's also important to meet the grid code requirements, and especially that can also potentially add to the cost once you haven't managed these.
Okay.
So also so that's why I think this part
you are surprising by that. Oh, still, I'm happy that you say that with all your experience, still there's a surprising in this project. Thank you very much, Hans, and also thank you very much, Andreas. So thank you. Yeah. Welcome back. Now, Hans actually did my work already. Introduction by our guest now is coming. And next to me, I have Gert-Jan Kramer from the University Utrecht. You are a professor from the Sustainable Energy, how do you call it? Supply. But you're also a chairman of the Sustainable Industry Lab for that. Welcome today. And here I also have Arend de Groot, which is our member from ISPT. We know each other for long. And Arend, you are the senior consultant of TNO for green hydrogen, especially specialized in the PEM electrolyzer technology. And today we also have Thijs de Groot from ICC, which is online presenting because he is also assistant professor of the Technical University of Eindhoven, which is of course also important to teach the students. That's why he cannot be there in the studio. I would like to ask Gert-Jan to take us through the journey. How can you understand what you need to do for the innovation to get there to a certain point that is commercial available? So Gert-Jan, please. Yeah.
Yeah, thank you, Carol, for the invitation. And I'm glad to be here at the end of what for me has been a truly wonderful project. We had the opportunity with co-workers Anand Krishnan and Vincent Koning to look at how costs could plausibly come down for electrolyzers in the coming years and the coming decades. And so there was quite some in-depth work that we did on that, but I've been asked today to zoom out a bit and tell you what we think that means for basically the creation of an industry, right? The creation of an electrolyzer industry, which is enormously important to drive forward the energy transition in the decade and in the decades ahead. So that gives me my title, the buy-down cost of electrolyzer stacks. But really, it's about creating an industry and what it takes. And, while a lot of the technical focus is on an electrolyzer stack, and that's the high-tech component, we already heard in the previous talk by Hans, that when it comes to cost saving, there's just as much to be gotten from the electrolyzer. And okay, then we got our physical object, the electrolyzer, but mind you, that in itself is not so interesting or commercially viable. You have to combine it with green power to make green hydrogen, and that then is only part of a bigger effort to rebuild the renewable energy system. So we have to deliver it, but it's part of a much bigger challenge and a much bigger system. So to put it in context, I'll be speaking about buy-down cost. And to those who are not familiar with the concept, it's basically the cost that, shall we say, we collectively, oftentimes that's the government, but it might also be strategic investors, big companies with very deep pockets who can basically forgo the immediate commercial opportunity because it isn't there yet, and to invest early in this technology. A lot of that is needed, and the takeaway from my talk is that you're talking in total globally to bring this industry to life of a buy-down cost that is in excess of 100 billion. Now, these are enormous numbers, but put it in context, it pales in comparison to the 1 trillion that every year is invested, according to the IEA, into delivering on a net zero trajectory for the world. And that 1 trillion is by far not enough. So we're talking about 3 trillion. So it's a comparatively modest sum, but it's real money that has to be spent on real projects that all individually, by themselves, make sense. And that's what makes the challenge. So when you do, and our work was very much focused on learning curves. There's no better learning curves than that for solar panels, right? Solar PV. That has been monitored from the 1970s, and this is how it came down. You look at a cumulative production of solar cells, which started out with small panels, rocketry, rocket-based stuff in the 70s, and then onto towards the terawatt today. And in the meantime, prices came down from basically unaffordable in the 70s to basically commercially viable today. And all through that journey, every decade, there needed to be an incentive to do that buy down, to invest in something that is not yet commercial, but in the belief that we will need it one day, so we need to build more of it in order that the next one is cheaper. And you see that also for solar cells. A rough estimate is that here again, over 100 billion was invested before, sometime in the past decade, PV panels, solar panels became simply a commercial reality. Now, let's on the same scale look at where electrolyzers was. This is quite a sobering plot, right? So the good news is they've always been cheap, but they haven't become much cheaper. So, and this spans 5-6 decades, more than I and most of us have been alive. So electrolyzers have been around for a long time, but always as niche products. And now we're looking to get it out of the niche, create an industry for which the challenges are different. I don't have the time to go into detail, but that if it's not already clear to you, it will become abundantly clear today. So the cumulative production capacity that has been done is in 2020 something like 20 gigawatts that has been produced in all of the world over the past half century. It's good to know that the current annual production, it was 200 megawatts in 2020, and if I read Bloomberg correctly, 400 megawatts in 2021, and growing. Now, if you will, you might think that there's a learning rate here. It's certainly less than what we've seen with PV, as you would expect on pretty basic technology considerations, but that's good. It will come down. And I think the good thing that the ISPT project has done, it has proven that it is quite realistic, quite plausible that if the cost today, and this was their, this is my statement, it will be 100 billion here again to bring the cost down to commercial level. What the ISPT did in this project at the start of it is said, well, the cost, and this is all-inclusive costs, right? Turnkey costs, so they're a bit higher than what you find in the literature. They're in excess of 1,000 euros per kilowatt, but, and that's the updated design, it could very well come down notionally by 2030, when we expect many gigawatts to have been produced. They might come down by a factor of 2. I think all in all, that is a credible estimate. It is a credible reduction to something below 1,000 euros per kilowatt. But quite some work has to be done. If you look at it like this, you say, well, they seem to suggest that things are going way faster than the trend line. But then you might as well say, you know, perhaps we should see the first gigawatt electrolyzer as really the first of a kind, so the start of a new industry. And then perhaps, if you will, it looks like this. But my central point here was don't be mistaken. It takes a lot of effort to get anywhere near with what is usually seen as the commercially viable target number. I remember I'm a long-timer, an old-timer in hydrogen, and in the early 2000s, I remember that the DOE in America had a target for electrolyzers, $300 per kilowatt. In the meantime, it's still something like that. My own guess would be that if it's below 1,000, it will find a niche, but the further down you can bring the cost, the earlier it picks up. So that in itself creates an interesting tension. The higher the cost is, the longer you have to wait. The more you do, the lower it gets, and the earlier it is attractive. So there is a challenge, and that challenge is brought out because if we now zoom out, we work here around the idea that sometime soon, this decade, hopefully, who knows how many years from now, but this decade, we'll see sort of a turnkey gigawatt electrolyzer emerge. But that in itself is the middle bit of something that is essentially an ecosystem in making. So there have to be suppliers feeding into that. We've heard in the last talk that also electronics, power electronics, utilities, project engineering, all of that comes in. But towards the bottom of this, towards the bottom here, there has to be green power fed in to make green hydrogen. And then it in itself creates a tension where, again, we will be looking at subsidy givers, investors with very deep pockets to do a strategic investment in this. Because, well, many people have made the calculation, and I show it here, right? There's two main ingredients, right? What does an electrolyzer cost? How many euros per kilowatt? But equally, how much does the electricity cost? We can all bank on it that the electricity will be free because there's so much excess capacity, but it won't be free all of the time. So a real cost has to be incurred and has to be incorporated for that as well. What you see if you look at where's the sweet spot here, and I've sort of indicated these are numbers, euros. I'm finishing, Caroline. I see you looking worriedly, but this is my last slide. The main takeaway is here, we need to bring costs down for electrolyzers to below 1,000 euros per kilogram. And then basically I think this can be a viable business, but significant challenges are still ahead. Expect, based on that complex chart on the right, to be project-based subsidies for at least this decade, because before this is a fully mature industry that can basically live on generic subsidies in the same way as we now have for wind and solar. So that's some time to come. It will be costly, but it will be absolutely worth it and vital to the continuation of the energy transition.
Wow, thank you,
Carol.
Professor Gertjan. I am really happy to hear your conclusion that if you can succeed and work all the hard work we have done and it can be a reality, so we are below this €1,000. So I'm happy to hear that. Thank you. Yeah, and if you have question, a deep question, a detailed question, you can put it in the chat. We will answer. The team will answer it, and we also pick one or two of the questions if there is time available. Now we'll go back to the one who has to do the hard work, which is to start with the stack. Why the stack? Because the stack will involving the cost reduction of 1/3 of the whole direct cost of the capex of the electrolyzer system. So today I have Arend de Groot and also another family member, Thijs de Groot, not bound by blood, but by project and expertise. They will tell us more about the PEM technology for electrolyzer, where we can innovate to save this 50%. Thank you, Arend. And Thijs will do the same for the Alkaline. Arend, please. Yeah.
Thank you. Yeah, so to start with, we did. The question to us was to predict the performance of a commercial stack in 2030, because that's what we need for the advanced design of the system. What kind of performance do we have in 2030? And of course, we didn't start from zero, because there's a very useful exercise that was done by the fuel cell and hydrogen joint undertaking many years ago. But what they did was that they set targets for different aspects of the electrolyzer technology, for different technologies, but including the PEM technology. And that's shown in this table. Targets for efficiency, for reduction of scarce materials, for power density, for flexibility. And so we took a look at these targets for 2030, and what we did was that we looked at what combination of innovations is necessary to achieve these targets. And it's important to realize that these targets are partially contradictory, because we want to have a cheaper, we want to have it more efficient, we want to have it more flexible. And if you want a thinner membrane, for example, to increase your efficiency, you need to find solutions to increase the flexibility, because you need to reduce the gas crossover, or you need to reduce or increase the durability of the membrane. So these targets, which are shown in this table, are difficult to achieve, because we have to achieve them at the same time. What we did, and that's going back, what we did was that we translated the targets on efficiency for the system level from the fuel cell and hydrogen joint undertaking to what it means for the stack efficiency. And then we used simple electrochemical models to look at what combination of innovations can help bring this efficiency, but also the other targets, such as the reduction of the iridium loading, which is a very scarce material. What innovations are needed to achieve those targets? And for that, I use a scheme that we have, which is a kind of very schematic roadmap for cost reduction for the PEM technology shown in this figure, where we say, well, the first cost reduction, and that's a very substantial cost reduction, is not so much technology, but it's volume. Simply creating the volume in the market will lead to substantial cost reduction. If we want to go further in the cost reduction, we really need new materials, new components for the electrolyzer. But we're still using more or less the same architecture. But if we really want to go further in the targets, we need radical innovations, radical changes in the materials that we use in the architecture on micro and nano scale. And that is what we call the third generation. And the point here is that if we look at the targets for 2030, then we cannot fulfill that with the second generation. We really need quite radical innovations in terms of material and architecture of the stack. And that is important, of course, in the light of the fact that we're talking about very large amounts of installed capacity that we want to achieve, and that means proven technology. So, in addition to the challenge of getting the technical innovations and the technical improvements, we also have a challenging timescale for that. Going into the more specific innovations, and this is not an exhaustive list, but we're talking about things like a thinner membrane. Membrane is one of the things where you really have quite some losses. So making your membrane thinner will improve the efficiency. At the same time, as I already indicated, it brings new challenges. It brings challenges in terms of maintaining the mechanical strengths, in limiting the gas crossover. That's something which is very important if you want to operate your electrolyzer flexibly. You need better membrane materials with a higher conductivity. Very important, already mentioned, reducing the iridium loading. That's something that is absolute a must if we want to scale up to gigawatt scale in view of the current production of iridium. Many of these innovations are necessary to achieve these targets. So better catalysts, improved designs of electrodes, other types of coatings and recombination catalysts. And what we did was play around with these innovations in our electrochemical model to see which combination of the targets leads to, or which combination of the innovation leads to the required performance. Important, these are, and because we're talking about third generation, in many cases, innovations which are still in the lab. So we have a challenging scheme to scale that up to have commercial technology in 2030. This is all talking about, let's say, the square centimeter, the better catalyst, the membrane, the electrode. Of course, we also had to look at the stack itself. For the system, it is of course important to know how many stacks will you need for a gigawatt. If you look at the current stack scales, it's about 1 megawatt, which would mean 1,000 stacks and all the piping and control systems that go with that. So one of the things that we really looked at is how far can you scale up the stack, and that was something that Hans also kept on challenging us every time. Can you make it bigger? And well, we did a lot of analysis and discussions. We looked at things like heat management and flow and velocities. Looked at weight. What does it mean if you build such a large stacks? And in addition to the stack design, we also looked at the operating window. How far can we increase that? Because that's quite determining for the stack size that we can achieve. So, with all that analysis, we came to, let's say, a conceptual stack design. Of course, we didn't do the detailed design, but we did quite some work on looking at the conceptual design, and in the end, we provided the input to the gigawatt project based on these data. So one of the important factors is that we said we will go to a 10 megawatt scale for the PEM stacks in 2030. That's your building block for the system. We had quite some discussions on the operating conditions. 70 degrees is quite a step up from today's technologies. So based on that, we could provide the input to the gigawatt project. So the main result was that we put together with all these model calculations that we did, we substantiated a conceptual design for the PEM electrolyzer, estimated the performance, and it's in line with the fuel cell joint undertaking targets that I showed at the beginning of the presentation. But we in some areas also had to be somewhat more conservative than those targets, looking at all those contradictory targets that you try to achieve. So these results could be used in the gigawatt project, in the process design, and in the bottom-up cost calculations. But I'd like to emphasize, and that's also what was taken into account in let's say the cost calculations in terms of the risk factors that we took into account, that we are still talking about technology which is in the lab today. We're starting to scale that up. We're starting to test components on a scale which is relevant for the gigawatt project. For example, in the hydrogen hub project, a project that we do also together with ISPT, and that's a factor of 1,000, and the gigawatt scale plant is another factor of 1,000. So we're talking about very exciting challenges that we have ahead of us, Carol.
Yeah, thank you, Arend. I think if I can understand your story from this whole process, it was really hardworking and pressured by the project lead. But I also see you have a lot of fun. But most of the thing, what is the most important thing you have learned from this gigawatt? Because you have a lot of experience. So what's so special? Yeah.
There's two things. One of the things is actually the pressure of time that we have to get to this point in 2030, and the second is we have been working on all these topics, and really optimizing the whole system is something that is incredibly important to reduce the cost and understanding the interaction between all those.
So you have lots of variables in one time, but still you would like to get the optimum. But luckily the team is very close.
I think we made a great step with the project.
Yeah, we are proud of you. Thank you, Arend. So I have another brother of the stack, which is for Alkaline. Thijs de Groot is online now.
Yes.
Hi, Thijs. Yeah, thank you. Thijs is online here on the other side in Eindhoven. Thijs, could you please give us a short process for the Alkaline stack approach? How can you give us the guidance to reduce the cost by 50%? So please.
Yes, happy to do so, Carol. Sorry that I couldn't be there today, but I have to teach the new generation.
It's also important because they have to work for us. So
exactly. There's so much work to do. But let's go to the advanced alkaline stack design as we have taken for the gigawatt project. We've made this picture. Showing what the stack looks like. It's actually from the outside. It was inspired by a picture for the Lurgy electrolyzer, which some of the older electrolyzer enthusiasts will probably recognize. But from the inside, it's quite different in the sense that it has more advanced, especially the nickel mattress deviates from the Lurgy electrolyzer because we believe a nickel mattress helps in getting a better zero gap design. It makes use of a nickel mesh anode, a non-noble metal cathode, a plastic frame. That's also where it differs from an old Lurgy electrolyzer, an advanced diaphragm, and because of that, we are really able to get to a high performance, high current densities, much higher than what is typical, at least in the more standard alkaline systems. That's basically the stack design in a nutshell. And what I want to do in the coming minutes is basically walk through the design choices we have made. Obviously, this is still a hypothetical cell design, but we believe it's possible to have such a cell design by 2030, and that it's also the a good design. So for that, to do that, I want to walk through this table, where basically we have made a number of important operating choices. First important one is the operating temperature, set at 100 degrees Celsius, so relatively high. And basically, if you look at temperature, I think you can say below 80 degrees Celsius, the performance will be just too poor. The conductivity of the electrolyte is too low. The kinetics of the reactions become too slow. Above 100 degrees Celsius, corrosion becomes a major issue, also degradation of electrode coatings. We also, above 100 degrees, you suffer from gas crossover, which affects the minimum load of your electrolyzer, because gas crossover, flow of hydrogen to the oxygen side, is the major limitation for flexibility of alkaline electrolyzers. Because of that, we think a range of 80 to 100 degrees is what we want. And in this case, we have chosen the higher end. Pressure, I think, is a very interesting parameter in the sense that the pressure we have chosen deviates from what's currently in the market. Currently in the market, we see either 1 bar or we see basically 15 bar plus. And basically, we believe that 5 bar or 2 to 10 bar is more ideal. We think atmospheric has the disadvantage that you, even for large-scale systems, you get high compression costs and also very large gas volumes in your electrolyzer because of the atmospheric pressure, which limits, for example, your ramp rates. On the other hand, at very high pressures, above 10 bar, again, this gas crossover issue, which I previously mentioned, kicks in, and that limits the flexibility of your electrolyzer. So I think with 2 to 10 bars, we are in the right domain, and connects to do that is also the separator. The separator, by operating at a lower pressure, we are able to use a thinner separator, because also for the separator, thickness between 100 and 500 seems optimal. There are now coming thinner separators on the market, which is a good thing, but I think it will not really go below 100, just because of, again, gas crossover and mechanical strength. Cell design, the zero gap, that is, has already been developed quite a long time ago, also for alkaline system, but there is quite an optimization that can be achieved there. I think we can learn a lot there from the world of chloralkali, where the use of mattresses has really helped in optimizing the zero gap. So that's also why we have decided let's go for a zero gap with mattresses. Obviously much better than the finite gap, but also optimizing the zero gap. Then there's the anode coating, which might surprise you, shows none. There is very fancy literature work on new anode coatings, but we are still a bit skeptical on the success of those. We know that nickel electrodes are not great anodes, but with the small impurities that are always iron impurities that are always present in solution, we do get a good performing anodes in our normal systems. And these fancy coatings that are currently seen in literature, we still have our doubts that they will be able to survive the corrosive conditions that exist on the anode, because the conditions are fierce. In acidic medium, it's really hard in PEM, then you need iridium. In alkaline systems, it's a bit better, but it's still not an easy condition. So it's to find something stable there. It will be challenging to find something better than nickel iron. On the cathode side, there the conditions are much better, because basically we're cathodically protected. And ideally, we would like to avoid the use of scarce metals there that are also vulnerable to some impurities. And we see a lot of promising developments there. So we think that before 2030, we will see good non-noble metal cathodes developing. It could be rainy nickel, could also be other non-noble metal coatings. The frame is a PSU frame, so plastics instead of a metal frame. I think that just makes sense from a weight perspective. Cell area 2.5 square meters, comparable to basically current chlor-alkali electrolyzers, which I think is an excellent benchmark to use. Also comparable to some of the larger alkaline water electrolyzers that are already out there. We think going bigger will lead to a lot of manufacturing issues, also to heat management issues. So that does not really make sense to us. Going smaller, on the other hand, leads to extra rim basically of your electrolyzer, so also adding to your material cost. So we think this 2.5 is there for a reason, so we stuck with it. Cell thickness about 1.5 centimeters, mostly determined actually by the operating pressure, and the number of cells 335, quite high. And there's a reason, because experts from the power supply side have always said to me, you pay for the current, not for the potential. So try to get a high potential and try to keep the current low. And by putting more cells in a bipolar configuration is then the way to go. However, at very high currents, very high cell number of cells, we do get the issue of stray currents, and that should also be avoided. So we think at about 400 is about the maximum you can get. I think one question some of you might have, is that high current density really feasible with an alkaline system with non-noble metal coatings? Is that realistic? Well, it has not been achieved yet with this system, but that's why I want to share briefly with you what it's based on. It's based on some experimental data that have been achieved at the BTU Cottbus, where they have the setup that is shown here below. That setup was operated at lower temperatures, up to 70 degrees Celsius, and with a thicker diaphragm. We have extrapolated those data with expected performances for higher temperatures and thinner diaphragms, and based on that, developed our electrochemical model. That model is currently, we have written that in the manuscript, is currently under revision at the International Journal of Hydrogen Energy. So I hope we can publish it soon, and then you will also be able to scrutinize it and determine for yourself whether you think it's realistic, that this current density is realistic. That model, that manuscript also contains a gas crossover model, because also gas crossover is a critical aspect for alkaline electrolyzers. And that's basically where I want to leave it. So with that, I would like to go back to you, Carol.
Question, as a technology developer, what do you see as a low-hanging fruit for high CC, for example, to improve the first step?
Now, we at high CC, we are not an electrolyzer developer. So we
what do you wish?
The electrolyzers on the market. We see, I think, I mentioned this pressure. I think it just makes a lot of sense to develop alkaline electrolyzers that are in this mid-pressure range of about 5 bars. And that should not be that difficult. I think already brings significant benefits.
Okay, thank you for your advice, at least. Yeah, thank you, Thijs. I think you already answered the question in the chat, by the way, so thank you for that. I have 2 questions from the audience. The first one is to Arend. Arend, the question is, which components give most uncertainties? Are you testing new/better components on lifetime and performance?
I would say the most important issue is the catalyst. And one of the things that we really need to do is reduce the iridium loading by a factor 10. That's a big challenge, and that is in part improving the catalyst, of course, itself. But it's also the interplay of the different components, the electrode design, the membrane. So it's not one single component where I would say that it's the issue.
Is it a system? You combine them.
It's the combination of the design of those components. With respect to the question of durability, yes, I mean we can achieve the best performance for a very short term, but that doesn't tell us anything.
Yeah.
So durability testing is an integrated part of the testing.
Yeah.
But it's challenging because it takes time and it's costly to do a lot of durability studies.
Yes.
But yes, it's a very important part.
Yeah, I know from another project which you're also part of is the high scaling project from high scaling, which we are also doing methods to do this type of lifetime performance. So somehow the trade-off you will also consider to that.
Yes, that's a good point. What we're working on at TNO, but as a community also, is to develop accelerated stress test protocols where we can do tests on a shorter, over a shorter period of time to look at what the impact on the lifetime on the longer term is. But to validate those, then you also need to do the very long runs, and that's something that is important not only to do on the small scale in the lab, but also on the megawatt scale or the 10 megawatt scale as we were discussing. You need to run.
Yeah. Oh, no, I'm waiting for you. The megawatt test center is already in Groningen, so for next year, I'm looking for your results for that. Yeah, thank you, Arend. So I go back to the next questions, is to Gert-Jan, Professor Gert-Jan. The question is, how to innovate, implement, and reduce cost going to the third generation when the second, sometimes the first generations have not even provided enough historical data on lifetime, performance, etc.?
Well, that's a brilliant question.
That's good.
In many ways, also the million or the $1 billion question.
Yeah.
I noticed that Arend, in the typical fashion of a researcher, put the first generation in 2020 and then every 5 years. But things have a nasty habit of taking a bit longer. I think with electrolyzers, we have a technology at hand which must be at a gigawatt scale, many gigawatts in the next decade. Because if it isn't, the whole rollout of PV and wind will stall. Now, is that comfortable to any investor in this realm, whether it's an electrolyzer manufacturer or a project developer? No, I think fundamentally not, right? So we have to do this in a pressure cooker environment, where basically, I think, going from one technical generation to the next, we collectively, and that's a very problematic saying, because who is we collectively?
Yeah.
But the whole industry and all those stakeholders have to somehow work together to take risks, which every step of the way feel just uncomfortable. Right? Because if it wasn't under time pressure, then this could easily take many decades.
Yeah.
I've done, and I think you want me to finish. So
no, we have time. So please explain.
Okay, well, I've looked already a decade ago at sort of what is the typical timeline of deployment of new energy technologies, and what comes out of that is historically we see an order of magnitude scale up in a decade, which is 25% yearly growth. And that's quite difficult to keep that up for 10, let alone 20 years. But if you contrast where the electrolyzer industry is today and where the European Union and all the target setters we should be in 2030, then you're looking at an increase in just 8 years of a factor 100 or more. And then still more in the next decade. And I think this indicates that this is will be development, technical development and deployment simultaneously in, well, again, a pressure cooker environment.
Yeah.
And how we do that, I think, is a collective challenge. And I think that's why projects such as this are great, right? Because you bring a lot of stakeholders together. So going forward, I think there's a good reason to build on that and build it out.
Thank you, Gert-Jan. It's really great explanation. Also, indeed, what is we? You have to do it. The whole supply chain needs to move. So it's a challenge, but it's not undoable. we have to start it with.
Yes.
And do you also have not a quantity but a quality advice or experience from yourself, also from Shell period? When you're working for solar and for the offshore winds, what can we learn from that? And because hydrogen edge, another challenge is that we need it now, actually, and it's much more urgent in that sense. Is there something you learn or you can think about that can accelerate?
Well, so I think it is important that governments step into this, right, with money, because this is clearly a sector that needs subsidy, right?
Yeah.
That goes back to my point of the buy-down cost. I think we have indications in this market that China is very active in this field. It would be good if Europe set something comparable next to that. That sort of competition will in itself be very healthy. And then, that's it.
Okay, so Arend, you would like to add? Yeah.
I mean, we're talking about the gigawatt scale today, but of course, a gigawatt plant is an enormous risk. So, what kind of intermediate steps could we? Are we talking about the right scale then for the
the steps we take? Yeah, is it the right step to take?
I sort of lost track of what I was going to say in the previous one, but I think before you go, so the projects are now at the tens of megawatt scale, and before you go to a gigawatt, it's only logical that you go to the hundreds megawatts. We know in the Netherlands and elsewhere, FID will be taken on that type of scale project. I think the challenge, the real challenge is when will people feel comfortable, decision makers, to take the next step? Because it is logical to first get in the learnings from the 100 megawatts and see how it performs in an actual system. Because mind you, the challenges for electrolyzers now are different than what they ever were in the past, right? Much more dealing with intermittency, which doesn't necessarily fit easily technically with what an electrolyzer would like. So that's a challenge. I think for governments, coming back to how do you feed money into the system, on the one hand, I say that they should do it in a manner that will inevitably be too fast, too irresponsible, but they have to walk a very fine line here, because at some point, with all the taxpayer money, the taxpayer will ask, well, how is it, is the money really well spent?
Yeah.
So that's a very challenging task. And I think also that I, as a scientist sitting in academia, try to feed and help politicians and decision makers in government to steer that course, to speed it up, but also speed it up in a manner that is sustainable
for longer
after the next election cycle.
Good.
Yeah.
Good. Thank you, Gertjan, and also Arend, for your active contribution. Thijs, also thank you very much. I think one of the industry is HCC, which is building from the tens to the hundreds. So there are people who are there to jump this hoop. But of course, we need to do it and supported by the government as well. Thank you for the Arend and also Thijs de Groot and Gertjan for today. So I will go to the break for a small 10 minutes and we'll come back to the power. See you then. back to the studio and also to the conference. Now is the time we are talking about the most surprising theme of the design, which we could reduce the cost by a large number, which is the power supply and the power electronics. Today I have here Nick de Koster from Yara. He's the lead, competence lead of all projects within Yara internationally for the electrical parts and the expertises. And online we also have Thomason, but he is not Thomas Hersink. He is not here yet, but he will come join us in a minute. So I will start to introduce you who is making this power part is happening for the cost reduction. So Nick, I would like to invite you to get to us through this part of the reduction you have done with the team.
Yeah, thank you for the introduction, Carol. Yeah, I will try to tell something about the grid connection. It's a plant based in the Netherlands. We have agreed with the stakeholders to have a connection point at the 380 kV substation in Borselen, in the Netherlands. Yeah, why Borselen? Borselen is close to North Sea, and at the North Sea a lot of renewable energy from North Sea is arriving. And also at Borselen we have a perfect 380 kV infrastructure. So that is why we have chosen for Borselen. Why you need to choose a connection point? Due to the fact that the design really depends on where you connect. And this had to do with all the grid parameters. For designing the plant, we needed input from the grid supplier or the grid operator in the Netherlands, which is TenneT. TenneT is the grid operator for the 380 kV, 150 kV voltages within the Netherlands. Yeah, where we had to look after. One of the things was the harmonic limits at the point of connection. If you would have asked me this 20 years ago, the harmonics limits were not the first point to think about, due to the fact that 20 years, 30 years ago, the number of semiconductors or non-linear loads was much less than nowadays. And definitely for such a plant where we need a lot of rectifiers, the harmonic limits are very important. If you look to the harmonic limits at the point of connection, TenneT gave us some restrictions with respect to those limits. The starting point is the IEC standards and the Dutch grid codes. The IEC standards, the 61,000 standards and the technical reports, that's really the starting point. Besides this, TenneT also had a list with limits for each and every harmonic from the second up to the 50th harmonic. So we also had to fulfill those requirements. And what is also very important is those requirements were for all kind of operations. So in this case, we really had a flexible operation from 0 to 100 megawatt, I wanted to say, but to 1 gigawatt, of course. The numbers, they go everywhere nowadays. So it's 1 gigawatt. And for each and every operation point, we needed to stay within those limits. And that was quite difficult to achieve. I will come back to the harmonics limits in the next sheet. Another thing is, if you want to do design and stay within the limits, you need your harmonic impedance envelope. So basically, to be compliant, you need to have the impedance for each and every harmonic. So that is also what you need to ask to the grid supplier. Of course, the design short circuit power of the equipment in order to select the correct equipment, that is really needed. Minimum and maximum short circuit power, 3-phase and 1-phase is needed. You need to have this for selecting the proper protections, but also for making calculations, short circuit calculations, and in order to select the proper equipment. Of course, maximum available voltage variation, voltage drops, what is still okay for the grid supplier. And based on that, you need to do your calculations. And of course, the grid and the transport capacity is very important. Now, if you look to some input we got from TenneT, is that you see on the left picture is that for each and every harmonic, you see that they have a kind of a planning level, which you see in the second column. There you see the planning level of the harmonics for each and every harmonic. And at the bottom of that table, you also see a limit for the total harmonic distortion at the point of evaluation, at the point of connection at TenneT, at the 380 kV. Of course, they have a planning level, and due to the fact that the 1 gigawatt plant is not the complete apparent power at that substation, there is a factor, and that is the one in blue, and that factor is applied to the planning level, and you can, and then the total harmonic distortion, you are allowed to make at that point of connection. That is the limit where you have to take care of. On the right hand side, you see the impedance envelopes. There you see for each and every harmonic, because each and every harmonic can have different impedances. So you need to take care of those during your calculations. If we go to the single line diagram, there we have looked in several kind of topologies. We looked into a 380, 150, 66 kV topology. We also looked into a 380 to 66 kV topology. What is important to select the correct single line is of course the costs. And in this project, we really looked into minimize the number of voltage stages, because each and every voltage stage needs transformers. Transformers costs a lot of money, and also transformers, each and every transformer, you have a certain kind of efficiency loss. So you really need to minimize this. And that was a basis for the design of the single line diagram. Also reliability, we looked into the reliability. So the less components, the higher the reliability. And we looked into the efficiency, I just explained. The higher the voltages, also the less the currents. And if current is less, you also have less losses. We looked into this, and you see in this table, you also have to look to the availability on the market, because you can select equipment whatever you want, but it needs to be available on the market. At least it needs to be available in 2030. So to those points, we ranked all those topologies. We ranked them based upon the points I just mentioned, and we came to the following single line. You see on the right-hand side some single lines we discussed with the team. And basically the recommendation was that, okay, we will go from a 380 kV from the point of connection with TenneT. We go to a 380 kV, a 3-winding transformer, to a 66 kV, and to a 66 kV towards the rectifiers, the transformer rectifiers, and in some cases also harmonic filtering and static commutators. But Thomas, my colleague, will come back on that later, so I cannot tell too much because otherwise Thomas has nothing to do. And one of the things we also discussed is that the balance of plant, so basically all the other consumers needed for the electrolyzer plant, we try to disconnect them from the electrolyzer part because they are causing the harmonics and they are causing the disturbances in the grid. So you really do not want to have those disturbances at your other consumers because that will cause problems. So that's why we have chosen for a 3-winding transformer. So the third winding goes to the balance of plant. And due to some short circuit issues, there is an additional transformer from 66 to 10 kV. And then you typically go for your low voltage consumers with a transformer from 10 kV to 400 volts. And that is basically what we have done with the team. So the team was Thomas, and Thomas is there, and Carla maybe also joins. I don't know. Thank you.
At least Carla worked very hard for this. This is what I show. Nick, I have a question, because now you're really doing smart design for power supply from the point as an end user, like say the one who is building the hydrogen. So you even avoid the disturbance in the grid. So you design a system which is avoiding. How does it work in the reality? For example, how to join efforts with TenneT, for example, in the Netherlands? Is it something you already discussed within the project or within Yara?
Yeah, basically for each, and as I said, 20 years ago, all the loads were more or less completely linear. Mm-hmm. So there were no issues with harmonics. Nowadays, especially for electrolyzer plants with all those rectifiers, this is really input you need to have from TenneT.
Yeah.
So as from the starting point of the project, this needs to be discussed. And there are a lot of parameters you need to take care about. Because what is important is not only the type of rectifiers, but also how do you operate your plant. Yeah. Flexible load, yes or no. Okay. And that flexible load is really a demanding thing with respect to the harmonics. Yeah. So you really need to take care of that.
But this is something will become very important, of course, when we're going more in electrochemistry with electrolyzer running plants on gigawatts. So thank you for this special knowledge. I'm a chemical engineer. For me, it's very difficult, but I try. You also can follow for the expert online. Now we also have, I have to peek on the name, Thomas Hersink Olesen. You are in Denmark. Thomas, welcome. So could you please take us through the power electronics? Because Nika gave you the homework to explain further. Yeah, thank you.
Thank you, Carlo. Luckily, I knew around the homework prior to Nick mention it, because otherwise I'd been a little bit stressed if I should prepare it already just from the glance, you can say. So I've been giving the topic around the I believe it's called here power electronics. I've put it into three subjects: power converters, the demand from the electrolyzer, and the grid code requirements. So, and there are you could say, quite linked to the points of the discussions as Nick have raised. Could I have the next slide? Thank you. If you take basis in the single line diagram that Nick just, I believe, showed on the last slide, what we have to talk about here is mainly around the two green areas here, you can say. This is comprising of the power conversion. And within this, you will first have a two-winding or at least a transformer that is stepping down the voltage to a low voltage. It can be in various configurations. It can be either liquid-filled or it can be dry-type transformers. It can have one or two or maybe even up to 4 secondary windings, depending on the configuration of the power converters. As well, there will be either one or several power converters connected to each secondary winding. This is, you can say, the main topology. And as you also see here at the signal line diagram, also briefly touched by Nick, is also that it could also comprising not directly connected to the power converters, but due to the choice of power converter, you could ending up needing harmonic filters, comms, shunt vectors, or other kind of compensation equipment. I will come back to that in a couple of slides, but just want to mention and make people aware. Could I have the next slide? Then the power converters. The power converters is the converter that will transform, say, or convert the low voltage from the secondary winding side of the transformer into DC that you're able to feed into the electrolyzer. Most of these kind of converters are either fitted with what we call thyristors or ISPTs, which are two power electronics which have, you could say, different properties. The thyristor is a component you're able to determine when you need to start leading the power, and you are cannot determine, or you cannot at least not decide when it stops. You can say it determined by the frequency. ISPT is a switchable component which you can turn on and off. This give you could say, certain advantages, which I will explain in the next few points. You can say first coming to what we have called the SCR converter, which is the classic diode bridge. That's just a three-phase diode bridge suited with thyristors. So again, as just explained, you're able to control when it start leading current, and you can to some extent determine when it stops. You can say it is cheap and efficient and very reliable, but could give you some challenge if you having a power that is you either have a requirement, and also mentioned by Nick, if you have very flexible either hydrogen demand, or you have very flexible you can say or fluctuation power from like a wind turbine or a PV power plant. Then you can add an ISPT chopper to this, and then you get a little bit more flexible converter. You can also go all the way, you can say, and go with an ISPT converter type, which give you much more, you can see at least a more flexible solution when you look into the harmonics and the reactive power requirements. And you also becoming more flexible depending on how you want to operate each of your electrolyzer that are connected to each power converter. Next slide. Then on the user requirement, then again coming back to the electrolyzer here, you can say the electrolyzer, it's as shown here on the tables and above, you can say, and also explained earlier. you have a electrolyzer which consists of a number of electrolyzers or modules that stack on each other, you can say, and to both depending on the size and the number of electrolyzer module you stack above each other, you need to apply a certain voltage and certain current, both at the start of life, end of life, to get expected hydrogen output from it. I can say I will, and by this, the electrolyzer itself is quite flexible, and you can say the power supply is also to some extent quite flexible. But I believe that we could at least encourage people to look in the direction of that you're optimizing, you can say, when you're looking at how you build up your electrolyzer, that you also have an eye on the limitation in the certain type of power converters that you have decided yourself for using, you can say, because then you might be able to, you can say, optimize the use of the actual power converter. And I also believe, as mentioned by Armand or Thijs earlier on, is also that you can say to some extent the potential is relative for free, where the current is really what you pay for. So if you can increase the voltage at least to a certain extent when it's still controllable and then meet the power converters available and so on, you can say that then you will be able to get more power out of your system without necessarily adding additional costs to the power conversion, you can say, or at least only minor costs compared to what you actually will gain from it. And then also, as mentioned earlier in the presentation, of course, what is also important from the user requirement point of view is to make clear is that how do you intend actually to operate this plant or these electrolyzer, whether it be operated on constant hydrogen production or constant load or constant power from the grid, or do you intend to operate either the plant or each electrolyzer very flexible? This is something that have a huge impact both of the, you could say, recommendation and towards what's the right power converters to use, but also eventually for which kind of equipment you will need at the end of the day at your electrical substation to be able or allowed to consume power from, in this case, the Tenet 380 kV grid, but you can say to whatever grid, of course, you're connected to, then you will be facing that you need to add components potentially. Could I have the next slide? Yeah, thank you. Because I think that here this is the grid code requirement, and here is exactly as just mentioned. You can say if there will be, as also shown and mentioned by Nick, there are certain requirements you need to fulfill, otherwise you're not allowed to consume power. And this needs to be met ultimately at the grid connection point. You can either, to some extent, mitigate this by choosing one or the other power conversion technology. But if this is not sufficient, you need to add other passive harmonic filters. You might need to add shunt reactors or ultimately active filter or statcoms to be able to obtain so the harmonic performance that the grid code supplier or tenant in this case accept for the grid. Also both because we will, you could say, push harmonic into the grid. And also mentioned by Nick, 20, 30 years ago, most of the load was more like a ohmic resistive load, you can say. But today, now we connect electrolyzer, but also turbines, PV, even the diode bulb you have in your kitchen are all non-linear load. So the grid connection people are facing a huge challenge due to this unlinearity of the load, and therefore, of course, they need to push requirements for the user to fulfill. Otherwise, the risking an unstable grid, and of course, an unstable grid, none of us have an interest in, because you're then, first of all, not able to produce hydrogen. But secondly, and probably even more important, then you're risking losing electricity at your home, and I guess nobody wants to do this, you can say. So, yeah, that was
your homework.
My homework, yes.
Thomas, thank you very much for your explanation. I'm just curious, because you are the lead engineer for high voltage electrical from Ørsted, so you have both sides, the knowledge from the power, but also as the future end user for the electrolyzer operator. So when you have the trade-off between CAPEX and this investment, and also the operational easiness or the wish you have for example, hydrogen production, how do you deal with this type of design in the real design choices in the real life, let's say?
It's an extremely good question, and a little bit, at least, difficult to answer, at least because we do not have a lot of or close to no hydrogen electrolyzer in operation, you can say. But what is extremely high on, you say, our agenda, might not for the first generation, because I think everybody needs to accept that there will be a certain learning curves to get such electrolyzer up and operating, is that these units really become something that can operate like an offshore turbine. So more or less without any interaction or direct interaction with any kind of civic technician or human being, so to say. Because otherwise, a 1 gigawatt plant will never be able to operate, you can say, because then we, particularly not, because at least I envision that the first generation, or there will be some hydrogen plant onshore, but I could easily also envision, also together with this energy island concept, which Ørsted also is a part of, is that these will be placed offshore, and then it will become even more difficult to bring people out there, or then you, like an old lighthouse, you need a small house, and then bring a family that can fish while they're not maintaining the electrolyzer. It's probably going to be a bit difficult to convince that family to live on a remote steel structure or artificial island in the North Sea. So what I'm trying to say is that I believe that the OPEX part, you can say, one thing is the efficiency as such, but I believe the maintainability or the robustness is probably maybe even more important, because you need to be able to put them out a little bit like a turbine. So it's like the fewer component, the better, the less valve or things you need to adjust, what can corrode. And things like this is really important, trying to avoid, you could say.
Thank you for the great opportunity as well to living on sea and fishing while you're working. So there's one opportunity to think about. I also have...
It could be for some, yeah.
Yeah, you have to tell me when the job is there, yeah? Okay, now we have also a few questions from the audience. I just, looking at the time, we have 5 minutes left. So one of the questions is, what is the biggest step to make the power supply cheaper? Who would like to answer? Nick? Maybe?
Yeah, I think this is a question for me. This is the power supply. Good question. It's more or less the same as what Thomas said. The voltage is more or less for free. Current costs money. There is a lot of material involved, copper or aluminium, and we all do know that this really costs a lot of money. So what we try to do is keep voltages high, so reduce the costs of copper, aluminium, etc. Yes, we do know that the higher the voltages, the equipment becomes also a bit more expensive, but that is something you need to calculate what costs more, yeah? Insulation levels or the costs of materials like aluminium and copper. That's one thing. And what we also try to do is to reduce the voltage steps. And by reducing the voltage steps, yeah, you're also reducing the number of transformers. Transformers are typically a high cost. And you try to avoid that as much as possible. So yeah, we kept the voltages high, yeah, and reduced the number of voltage steps. And an additional thing, an additional benefit of avoiding voltage steps is you are losing less energy. There are less losses due to the fact that you have less voltage steps, because each and every voltage step introduces an additional loss.
Okay, that's great. So it's not only the capex you have to invest for the steps, but also the efficiency you try to protect.
It's indeed always a balance between the two. Yeah.
Great, thank you. I have one question I think we still have time for. How to control the power supply, for example, megawatts scale of stacks. Is this primary voltage or current controlled? You again?
That's Thomas.
Oh, Thomas, please. How to control the power supply to the stacks?
Ultimately, you will get, this is the hydrogen output, the expected hydrogen output that will need to control this. So you will get some kind of feedback loop from the electrolyzer telling you the potential you need to raise over the electrolyzer, and then you're producing hydrogen from this, you can say, and this is pretty controllable and something the power converters can do. One thing I maybe forgot to mention is that these converters that we expect to use is, you would say, commercial available. So this is like converters used or intend to be designed or used for an application like a PV or large industrial drives. So we said drives that is working and to say type tested and can do this because again we just basically need to deliver the power to the electrolyzer, and then the electrolyzer do the rest of the job, you could say. So.
Good.
I don't know if this answered the
it is a difficult question, of course. How it is, because it's
a little bit.
Yeah, what I also learned today from you two, as expert from the power supply and also the power electronics, is that there is also a lot of smart design we can apply, really depending what is the trade-off for your investment or your maintenance, your operational, and your preference, how to operate such a plant and in which extent of chain. So thank you for that, to letting us know how to being smarter and cheaper to build these power electronic blocks for that. Thank you very much, Thomas and Nick as well. So after this power block, we will go for the next, which is the balance of plant. So I will invite you soon. Welcome. So we are back to the last part of the most cost saving, which is the balance of plant. So today I have here Paula Granados. I try to exercise Mendoza. Paula, you are always our Paula, so I never have to recognize your last name. So Paula, welcome. Paula is the technology developer of a high CC for green hydrogen. Welcome, Paula. And next to me, we also have Rink Zwerver from Gas Unie. So you are the compression expert of this expertise. So today, you two will explain the last bit of the cost saving, which is the balance of plants. So Paula, I will give you the word to start with your approach how to reduce the cost by balance of plants focus and separation.
Yes, thank you, Carol. Indeed, I will talk about the balance of plant and focusing on the separation section. I will focus on alkaline technology, although the learnings might also apply for PEM electrolysis. So before I dive into specifics, I would like to first start with an explanation of the functions of the separation section, because you can obviously think a separation section is there to separate just the liquid and the gas that are produced, but there are also other functions that this section should fulfill. So among those are also removing the excess heat that is generated in the electrolysis section, and obviously that the separation section then it also helps circulating the electrolytes to and from the stacks. This is also the point where the fresh demi-water is added to the process, and also helps to cool down the gases and to remove the impurities in the gases like KOH, etc. So here you see a block diagram of a separation section. So if we focus, for example, on following the path of coming from the stack, so if we see the cathode where the hydrogen is generated, it exits the stack and it's been sent to a gas liquid separator. In this, the two phases are separated. The liquid electrolyte is then recycled back to the process via a catalyte pump and is cooled down before going back to the stacks. The gas that is coming out from the gas liquid separators is sent to a scrubber where is washed, impurities like KOH are removed. The condensate is recycled back to the separator, which in turn ends again back in the process, and here also the demi-water is added to the system, and the gas that it exits here is sent to the compressor. There is a similar path for the case of the oxygen, and in this case for this project, because we don't see, we send this basically not to a compressor but to the vent stacks. So what I would like to talk about today is the design approach, and I split it into 4 topics. So I will talk a bit about our methodology for sizing the gas liquid separators. I will talk about how we optimize the modularity, how we selected materials, and how we selected equipment. So to start first with the sizing of the gas liquid separators, again, I would like to also make a short explanation of what are the functions of the gas liquid separators. And as I said, the gas liquid separators are there for the separation not only of the gas from the liquid, but also the liquid from the gas. So the reason for that is that you want to have the least amount of liquid carryover on the gas, and you also want to have as little as possible gas be recycled back to the process. For this case, we chose horizontal vessels, and we developed a method to estimate the minimum required residence time that is needed to fulfill these 2 functions of separation. We took different parameters and constraints into account, such as the gas holdup of the stacks, a reasonable assumption for bubble size distribution and flow patterns, etc. Now, another function of the gas liquid separator is also to equilibrate the pressure between the anode and the cathode size of the stack, and this is done via a balancing line. A balancing line is basically a pipe that connects the 2 gas liquid separators and makes them as communicating vessels. So what you can imagine is that you want to separate, you don't want to mix the hydrogen and the oxygen because, for safety reasons. So in case there is one of these separators is, let's say, the liquid is sent to the other separator, you want to avoid that there is mixture of the gas, which is the problematic part. So for that, it is sensible to choose a liquid field fraction of higher than 0.5. That is also to ensure the safety. With respect, also another function of the separators is to act as a light buffer vessel. And what I mean by this is that when the stacks are operating flexible, there is a point that, for example, they are operating at a lower load, or even they are shutting down, and that means that all of a sudden you have you stop the gas production. You have a stack that is full of gas, but that you need to replenish with the liquid. So that means that the vessels, they also need to provide that liquid inventory for being able to replace the gas in the stacks with the liquid coming from the separators. So that also helps for the flexibility of the process. Now, in this project, we optimized the modularity. So we looked at the costs of the separators for different module sizes. So if you connect 2 stacks, 4 stacks, 6 stacks, 8 stacks, etc. And we found that there is an optimum of around 8 stacks connected to a gas liquid separator. Coincidentally, this is also the starting point for the baseline design, so what the first part of the work that we did. But you have to think that the stacks here are much larger. So we are talking about 8 stacks that have a significantly higher flow rate. So that means also that in essence, what we managed is we managed to reduce 10 times the residence time compared to the baseline design. So we have very large modules in that sense. So here in the picture you see basically how an advanced module looks like, where you have the 8 stacks connected to the gas liquid separators. We chose also for separate circuits, so meaning that there is one circuit for the anolyte and one circuit for the catholyte. This is also to help in preventing mixing of the gases as well. So when you look at the table, comparing the baseline design and the advanced design in terms of the number of the amount of equipment, you clearly see that there is a big difference. So that we go on average from, for instance, 48 hydrogen gas liquid separators to only 6, which is it's a significant reduction, and that translates also in reductions of costs. One important aspect that we had to consider is the material selection, because we are talking about, in this case, for the alkaline electrolysis, we have a concentrated electrolyte, so 30% KOH. You also have the gases, oxygen, hydrogen, but they operate at temperatures of up to 100 degrees. So this is a very corrosive environment. So you have to be careful in selecting the right materials for this application. So what we saw is that the stainless steel 316, for instance, is not recommended for these conditions, or at least not higher temperatures higher than 80 degrees. Nickel and the nickel alloys are very suitable materials that you can apply for virtually all the elements in the balance of plant. Nickel clad or nickel lined vessels, for instance, they are also alternative as a cheaper alternative to pure nickel, for instance. You can also think of PFA or PTFE lined carbon steel as an option. There are also concerns regarding permeability of the gases through this material. So that's and that's one topic of concern. There are also certain duplex stainless steels that are suitable for equipment, but there are some exceptions, for instance, in the use of in combination with oxygen as well. Now, based on all this information, our approach then was basically to contact equipment manufacturers based on our specifications and make a selection together with them of equipment for this for the balance of plant. So we selected nickel-clad vessels for the gas liquid separators. We selected nickel magnetic driven pumps for the light pumps. For a case of the gas coolers, for oxygen, we have semi-welded stainless steel 316 plate heat exchangers, and for the light coolers, we have gasketed nickel plate heat exchangers. So now, I would like to finalize my presentation with these slides, thinking of what needs to be developed now to be ready for 2030. So what needs to happen now so that we can build these large modules in the future. First, I think one important part is that we need to look at the fundamentals. It might be surprising, but we know very little about the multi-phase flow of the electrolyte and the gases at the operating conditions. So we need to know more about, for instance, gas holdup in electrolyzers, the bubble size distribution, flow regimes. We need to understand it. Another aspect is regarding the process control. Connecting multiple stacks to one gas liquid separator is rarely done in practice. So you see some concepts, but it has never really been applied. So the flow control is also something that we need to ensure that is done properly, because you want to have equal distribution among the stacks. So that's very crucial. So we need to prove it. And then maybe the third point is regarding the supply chain. What we show is that building these gigawatt scale plants, we need to build larger modules. So just as a reference, the module that we see here is 160 megawatt size. And nowadays, modules are on the size of tens of megawatts. So this is like more than 10 times a larger module than what is currently now. So typically, when you think about, heat exchangers and pump, I mean, they can be as large as you want. But sometimes the challenge is on having this type of equipment with non-standard materials. So, for example, the nickel pumps, etc. So that sometimes is not so readily available in the market. So we need to also make it as well. So this is basically the message that I want to send through.
Yeah. Thank you, Paula. I think it is really good summarize also for the last part. Basically, I have a question. Maybe you already answered them partly. So you worked for a chemical company before,
yes.
Like say. So I think we have a lot of experts who is really working with a lot of experience for balance of plant, especially for separation parts. Yes. What is your advice by doing this project? What do we have learned which is different? Or you have to look at, for example, the risk having gas mixing, or do you have advice? What was new for you, for example?
What was new is that basically the proposal of this project is that we dare to think very large. So meaning that we go from a standard module of maybe 10 megawatts to a module of 160 megawatts. Yeah. So if you look at for example, the projects that HyCC is now currently busy, we are trying to develop plants of that scale. Yeah. Meaning that so we really need to make that big step of having
how to map volumes with the size in a certain chain.
Yeah, exactly. So that's kind of closing that gap between this conceptual design to actually apply that in practice. I think that will be one of the main challenges. Yeah.
But you do believe the larger size of the stack, it will help for the total cost reduction. So it's a step we need to look into.
It's definitely. I mean, we cannot build. It will be very difficult to build a gigawatt scale plants with the module sizes that we currently have in market, because it's basically it's a lot of equipment.
Yeah. Okay. Thank you, Paula, for your explanation. Yes. So I was looking at the Rinka when you say size doesn't matter for the pump. So I'm looking at the Rinka. If you see, you will say the same. So the last part of the balance of plants, I would like to ask Rink to lead us through the idea how to select when you have a wish to having high pressure hydrogen production. So can we do it smart and cheaper? No, thank you.
Thank you. Can I have the?
Oh yes, of course.
Oh sure. Sorry.
Yeah, okay. You are in charge.
So actually, starting out with the basic design, we selected the compressor equipment for that process parameters as it was laid back then. It was first 1 bar electrolyzer operating pressure and 30 to 50 bar grid pressure. So we started out with a lot of compressor units because of that low pressure, and we did try to find during the market consultation to find out whether or not there was a little bit of innovation going on to use centrifugal compressors for this application to reduce the number of compressors. Actually, there is innovation going on, but at this moment not mature enough to put in operation right now. So what we try to do is coming from the basic design to the advanced design to confirm the compressor concept selection. So we started out with the recip compressor. And we had to look, so is this still valid, or is there something we can do to select centrifugal compressors and then reduce the number of compressors. Yeah. To see what would be the minimum number of the size of the compressor units, and then also the minimum absorbed power for energy consumption. And then to see to optimize the process design to see whether or not we could find the ideal process conditions to match electrolyzer operating pressure and compressor performance. So there's obviously a very strong relation between the compressor design and the electrolyzer operating pressure, because the outlet pressure of the electrolyzer and the separated equipment is of course the inlet pressure of the first stage compressor. So as hydrogen has a very low mole weight, and the density is very low at the inlet of the first stage compressor inlets, the high compression ratio and the turn down behavior actually determines the type of compressor you will need. And we landed back at the reciprocating compressor type. Obviously, the compression ratio, if you reduce that is reduced with the increase of the electrolyzer outlet pressure. So at a fixed discharge pressure, the ratio will drop. Next, the absorbed power. If you fix the mass flow of the compressor, of the product through the whole compression system, and you will reduce the compression ratio, the absorbed power will drop. And then the number of compression stages, the number of the compression ratio per stage is limited by the discharge temperature. The API 618 limits that, or the newer version will limit it at 125 degrees C. So therefore, the number of compression stages is reduced by the reduction of the overall compression ratio. So that leads to the quantity of compressor units. These are reciprocating type of compressors. So those are of a displacement type, low inlet pressure and density. The capacity is limited by the number of the maximum intake volume. The intake volume is of course limited per cylinder, and each compressor frame can only have so much cylinders mounted on it. So the required capacity is then met by just simply meeting of increasing the number of compressor units. We can see that here in the table. So coming down from 1 bar suction pressure, starting over here to 30 bars, you will need in this case then the 7 compressors. Increase the pressure from the electrolyzers to 3 bar. Then the number is reduced to 4, then at 5 or to 2, and increasing further from 2 to 10 bars or 30 bars with the PEM electrolyzer types. Yeah, actually the number of compressors doesn't drop anymore. So as of 5 bars and higher, you don't need any less compressor equipment, but obviously the capex of the BOP will increase because of material cost and equipment cost. So as we say, as you can see in the table, from increasing the pressure from 1 to 5 bars reduces the number of compressors from 7 to 2 units, with also increasing the BOP capex. The number of units remain constant, coming up from 5 bars to 10 bars inlet pressure, and then the increase, as we could see, of the operating pressure of the electrolyzers and the BOP is no longer justified from 5 bars higher. You can see that in the bar graph over here again. So this is total capex and opex of the compression. And you can see that the sweet spot lies around here in the I would say around this 5 bars operating pressure. So and there's another item already pointed out by Gijs. By Thijs, if you increase the operating pressure of electrolyzer equipment, you will have also more problems with gas crossover in the electrolyzers. So that's also another argument to not increase the pressure higher than that. and I think the latest slide I have here. Yeah, for the if we would select this electrification type of equipment, there is reliability and availability parameters which would then push you to have an installed spare, which may not be the case if you would select centrifugal equipment. Always depending on the requirement you have for availability and reliability. So that's where we landed at 2+1 installed spare units.
Good. Rink, you are really well in time, so I have lots of room to ask you questions.
Thank you.
So, Rink, you have 20 years experience at GasUnie, so especially really specialized in this type of experience. How is your finding and experience in this integrated project like a gigawatt compared to the project you are running, for example, NOH2? How is your experience in this? What did you learn to working with different disciplines? Wow, your own discipline has a lot to improve and a lot to innovate, also especially in the design-wise. So what is your experience or your takeaway from doing this type of project integrated? Yeah.
So actually, the other projects we're working on is normally also multidisciplinary with the different, mechanical, electrical, and controls departments working on that. And actually, this project was not only interdisciplinary but also completely different product properties. Electrolyzer equipment, the high voltage equipment, the power supplies, the power electronics, but also the process equipment is that much different than any other projects I was working on. And it was an excellent team working with all excellent experienced people. So there was an absolute delight to work with. Absolutely. Yeah.
Yes. Okay. Yeah. Thank you, Rink. And also looking at the audience, they have a few questions for you too as well. So I'm reading out to the questions which is already in. The question about the balance of plant. Are there opportunities or possibilities to reduce cost for water supply? I think for Paula, this question. Yeah.
I suppose so. Supply of demi-water, I suppose, is the question about?
I think yes. As a balance of plant utility, I think that's mentioned.
Yes.
Yeah.
Well,
as a feed. Sorry.
Yes. So basically, the production of demi-water is it's. I suppose a quite mature technology. I don't see directly something to improve with respect to cost reductions. For that utility directly related to, for instance, the optimization that we have done during the project.
Yeah, within the scope, I think.
Yes,
but for example, making demi-water on level, especially for PEM, there should something we could innovate.
Yes, right? Definitely. So for PEM technology, where you have more stringent requirements for water quality, and also for certain alkaline technologies that operate at higher current densities, that could be definitely something to look at.
Okay. Thank you, Paula. So I select one for Rink also. What about the capacity control of the compressor?
Capacity control, because of, again, the hydrogen application, speed variation for this type of compressors is not available or not a good idea because of valve behavior you would get. So we were running fixed speed compressors. And then capacity control would then be realized through valve unloaders, but most probably by kind of a Herbiger unloader types. Yeah.
Okay.
Unloader hydrocom systems.
Yep. Yeah. Thank you. I also have a question, I think it's for Paula. How about the build-up of organic and inorganic components due to degradation and or corrosion mechanism?
Yes, so basically what one key point that we selected in the stacks is that we selected electrodes that are less susceptible for impurities. So you have a bit of less impact on the impurities that may circulate in the system. You have to think that's why you need to have a very conscious choice of the material selection that you have, not only in the stacks but in the rest of the balance of plant, so that you have as little as possible of leaching, for instance, of metals or other impurities coming into your system. Yeah.
Okay, thank you. So that's good to take it overall. Again, system integration and also the approach for the whole chain is very important, but we have learned from this project, I think. I have another question for Rink. So when you're talking about rotating equipment and knowing this type of high pressure hydrogen plant, which will come as a product or a requirement, is there any already market or working together with this type of suppliers?
Yeah, absolutely. I think this type of equipment for this application is not a really special equipment, right? It's your basic refinery equipment. So in this sense, most of the suppliers of this equipment are familiar with this operation, also these process parameters. Yeah.
And do they also need the knowledge for the specifications, because it will be used differently?
Actually, it will be used that you need to follow. I guess you know the power of the profile of the offshore wind park.
Okay.
So it will be a kind of variable loading of the systems. But again, it's not a really special operation for this kind of this kind of standard.
It's a kind of a known environment due to the power of the offshore wind, for example.
Absolutely, yeah.
Okay,
yeah
that's great. It's a great opportunity. That is already acknowledged there. Another question. I don't know if Paula can answer this as well. What is the approximately gas bubble fraction in volume percentage in lime out of the stack in full load operation?
According to our estimations, well, obviously this will depend on the current density, but at full load is something about 65% of gas holdup in the stack. So that is what is coming out from the stacks going to the separation section, basically.
Okay. Yeah. Yeah. Great that you know by heart. Another question is as well, you said in the beginning of your slide that the fundamental understanding of the mixed multi-phase gases is important. What type of work is already conducting at this moment to prove it or to bring it to a higher level of the commercialization?
Within, for instance, within the ISPT and HCC and other academic partners, we have a lot of projects that we look at, for instance, not only the modeling work, but also experimental validation of those models to see if we can understand better the multi-phase flow of electrolyte at different conditions. There are a lot of initiatives. Modeling is difficult because you have the challenge of not only modeling one gas bubble but modeling the whole electrolyzer. So that presents some challenges. And with respect to the let's say experimental part, having proper testing facilities to be able to gather the data that you require, and for instance the visualization of the gas bubbles at the operating conditions. So looking inside the stack is not so straightforward, for instance.
Okay, thank you, Paula, as well. So looking at the time, thank you very much, Paula, and also Rink for your contribution, but also for your openness and especially your expertise to share here. Thank you. So now I invite my colleague Andreas for the last thing, because if you heard this three-part, we have a lot of things we can do from the Gigawatt project where we have learned, but which type of focus do we have to do in the coming period? So that is something we can advise from ISPT point of view. Andreas could be our next guest to discuss about this opportunity. So I have Andreas here on the table, and also Hans entered the room. So the next step towards how can we really reduce this 50%, the good thing today is I have a lot of experts here in the room, and also the one who is not on the screen. So when an expert, and especially a technical person telling the story, then I do believe it. They are not good in lying. So Andreas, so please tell us how to approach these steps. To get there.
Yeah, who am I to tell this, right? I mean, you have seen so many experts come by, so really first want to give a compliment to the team for the delivery of today, and I hope you really enjoyed and liked this. Of course, you have to draw some conclusions and think forward. I mean, we have drawn what a gigawatt factory can look like, but it is not yet there. The largest electrolyzer factories are of the order of 10, 20 megawatts, megawatts or something like that. And we have to move forward. And if you look at what we see as priorities and steps to take from where we are today, the first thing is, well, like the famous slogan says, just do it. We have to find ways to really start building up our track record. We have to learn by doing, build factories. And you see, of course, there's many announcements, feasibility studies and FEED studies, and going forward from there to really start building electrolyzer factories at the moment. Often closely connected to industrial transition plans for refineries or chemical industries or others. And these projects are developing, and we hope to see in the next few years many FIDs coming to really start building and running factories and learn what it is like to run a factory in a flexible mode, for example. This all needs to develop to learn so that we are ready also to build the gigawatt factories really by 2030. Clearly there are plans for that, but the first steps we need to take first, I think. And of course, and it's been mentioned before, we need the conditions from the government to support that. I'll come back to that in the third point. So in the meantime, while we're building these factories, also what we've seen today, we've taken a bit of a leap of faith. There are still uncertainties in the technology. We need to think further, develop further, build and demonstrate that high-performance electrolyzers that we have presented today can really exist and work the way we think and dream that they can work. So from our point of view and the way we organize our innovation programs, we really have to look into these points, really build novel electrolyzers and dive into them and experiment and play and optimize and find stable technology at scale that can work. So improvements of electrolyzers are important. Clearly, we have a whole world of suppliers out there, but the supply of electrolyzers is not just a company that makes an electrolyzer, it is a full supply chain there. And like we've seen, for example, with PV and other technologies, there's a lot of high-tech knowledge there that can feed into this supply chain and strengthen that. And this is what needs to be further developed globally, in Europe and also in the Netherlands. It's something that we are working at already in some of our projects, and I think this needs to accelerate further across Europe and like everywhere basically, because we see the need for hydrogen at scale is so large that there will be so much technology need that we need to become professional and strong at delivering the technology that we need for our energy transition at scale and at volume. Another important aspect that comes with it is to think about the safety, of course. One of the big challenges going to this gigawatt scale is not so much that electrolysis in itself is new, but the scale at which we do things is new. And therefore, at these large scales, safety is key, is very, very important. And we have a lot of discussions amongst some of our partners and with our partners to really understand more what it means, safety at scale. I think this knowledge needs to be spread and something really to work together, because it's safety standards that need to be shared across the board if you want to roll out this technology at the global level. And then in the end, these factories have to work in an optimal way, and doing that with smart system integration, looking at dynamic operations. What do you do with the power into the electrolyzer versus power you supply for other use? How do you develop these systems so that hydrogen becomes affordable, cheap, and the whole system will work? I think there also we have things to learn. Now, finally, in the end, all of this is driven by the market. So we need to have a market for technology. We need to buy the technology. And I think some of the things that we've seen and learned in this project is that you have to think also in concepts of modular systems that you can scale by numbering up. And where is the balance? That was one of the questions we had when we started this project. And we've seen that some Alkaline scale, in our project at least, worked out to be around 160 megawatt, the number of electrolyzers as a modular unit that then you can repeat. is something that you can start to further elaborate and define. So define your standards, define your modular units, and therefore unlock the possibility for suppliers to offer products in these modular systems or to offer complete modular systems, combined also through multiple suppliers, because you have to go from the stack to the full factory. And across the board, we need to think how things fit together. And if you can standardize that, that will also again bring cost reductions and safety with itself. And finally, in the end, not only the market for technology offering needs to develop, but also the market for the green hydrogen. Ultimately, we just need to know that when you buy a green product, it's the product of choice. It's cheaper. It is the first thing to buy. And it shouldn't be a question whether green products are something you want to buy, but it should be the obvious thing. And for that, we need policies in place that support that. So this is a lot of the key learnings and conclusions that we drew over the years from working with this excellent team of people. We will be working on that. We move forward. I hope what we've shared with you today that you liked it. We wonder, hey, are you in for more? And if so, reach out to us and join us. You're more than welcome to participate in the work that we do. This is the message that I want to give across as a closure for today. But maybe there are some other remarks, questions to be.
Andreas. This is a really great list and a guidance, actually, based on our experience from ISPT with our partners, where we should work on. And I think we emphasized several times within this conference that we can do it. There is a road to do it, but we have to do it. And I got a question from the chat. What blocks us to build this in 2023? So it's a real good question. I don't know who raised this question. Maybe someone want to comment on the technical aspect, Hans, maybe?
The technical aspect.
Why not do it now, of next year?
Well, clearly, there are still quite some research and development and piloting and demos to be done for the innovative stacks and the design with the electrodes and also the number of stacks and the power ratings of these stacks. So that clearly needs to be done. So that should take a couple of years. Many other technical areas, like the power electronics, like the compression, like the balance of plant just now. I mean, that is already available, and with some minor which are improvements which have minor risks. We can also include this in a design and go from there to the economic evaluation. So because at the end of the day, it's also about.
So you already have tips. Economics. So with small changes, we can gain a bit of money, not 50%, but surely significant. Okay, so we have to contact now. Hans, for this one. Thank you very much. Today I'm really happy, and one of them is that we have all our experts here in the room and also in the room next to us with our partners who work really 3 years long hard, but really with joy always and openness to do this together, because they do strongly believe in green hydrogen. They have to fly, so they are willing to share the knowledge. That is why we initiate this conference today. So special thanks for the experts who contributed today, but also behind the scene and supported by the management from our partners. I think after this meeting, I don't need to explain that this will fly, but we have to do it together. So thank you for being here, and also thank you for the active contribution for the chat that make this session also valuable on both sides. So please let us know if you have more questions. We will make the slides ready on our website from ISPT. Thank you. Thank you, Andreas. Thank you, Hans.